It's a common assumption that the machines that power our lives were invented by us in modern times. But is this true? Today, new discoveries from the ancient world are forcing us to reconsider and to rethink the development of mechanical science. And what we are discovering is leading scholars to go back and rewrite the history books. These are the machines of ancient China. While Europe endured the so-called Dark Ages, ancient China reigned supreme as the world's technological superpower. Only now are we discovering that many of the inventions that shape our modern world have their roots in this remarkable Oriental civilization. Complex geared machines that allowed production on an industrial scale. Precision seismographs for detecting earthquakes. Drilling machines that bored for natural gas hundreds of meters beneath the Earth. The cosmic engine, a super-scale astronomical computer that not only told the time, but also predicted the passage of the planets and the stars. And even blast furnaces, capable of forging metal on a scale that rivals that of the modern world. Some of these technologies were so complex that for centuries they remained a mystery.
China was always an immense state, much more unified than Europe at the same time. If they were to control the population, they had to organize manufacturing on a very large scale. I regard that as the basis of industrialization.
But how did the technology of China become so advanced? And who were the ancient inventors that designed and built these complex and awe-inspiring machines? This ancient text provides a clue. It describes in detail something that is still needed in modern times, but was actually invented nearly 2 millennia ago. It is a seismograph, an earthquake-detecting machine. It was designed and built by the master inventor Chang Heng. Chang Heng, who lived during the time of the Romans, rivals Archimedes and Leonardo da Vinci as one of the greatest geniuses of the past. In the 2nd century AD, he designed the Hufeng Daidongyi, the instrument for inquiring into the wind and the shaking of the earth.
The seismograph isn't quite as modern an invention as people perceive. It was invented 2,000 years ago in China. Chang Heng's invention was probably something like 1,600 years ahead of what was done in the West.
Today, the Earthquake Administration in Beijing uses digital technology to record ground-shaking tremors over large bands of frequencies and seismic amplitudes. And an early warning earthquake system was just as essential in the past. News traveled slowly across the vast state. How could news of an earthquake be passed to rescuers quickly? Chang Heng's seismograph was the answer.
The device consisted mainly of a massive bronze vessel. This was reputed to be about 6 feet across.
The earthquake machine was a huge vessel of cast bronze, consisting of 9 dragons facing outward in a circle. Each dragon gingerly held a ball in its jaws. The instrument was designed so that any seismic tremor would cause the ball to fall from the jaws of the dragon and into the mouth of a frog facing the direction of the tremor. Despite its beautiful exterior, it is the internal mechanism of the machine that is so ingenious, even by today's standards.
When an earthquake struck, the vibration which was transmitted through the earth, which actually travels very, very quickly through the earth's surface, would hit the jar.
There was a vertical rod inside the jar, carefully balanced with a weight at its top end. This is known as an inverted pendulum.
The seismograph worked by having an inverted pendulum inside it that basically toppled over, and by toppling over in one direction or another, it would impact with a ball, and the ball would fall from the side of the seismograph, giving an indication from which direction the earthquake had actually come.
The inverted pendulum is an ingenious device. It stands motionless until the slightest vibration sends it toppling over, indicating the direction of the epicenter.
We can all picture what a conventional pendulum is. If we think of a grandfather clock swinging, it has a pendulum swinging inside it. An inverted pendulum is the exact opposite, where you have a pivot underneath and you're trying to balance that from underneath.
But there's another discovery from ancient China that, like the seismograph, is vital to us today. A technology that delivers the ultimate power source of the modern world, oil drilling. Today we assume that it was modern engineers who pioneered the art of deep drilling technology. Yet incredibly, the techniques used in acquiring supplies of oil and natural gas were actually reinvented from those of the Chinese 2,000 years ago.
It's amazing to think that it's 2,000 years ago the Chinese were using the same techniques to drill for salt and for natural gas that we're still using today.
The sheer size of the ancient drilling machines was remarkable. Derricks, also known as Heron carts, rose over 50 meters above the ground. Images which we associate today with the landscape of Texas would not have been uncommon in ancient China. Amazingly, examples of these ancient industrial machines still exist in some regions of China. This allows scholars a first-hand glimpse of the devices used in these ingenious, super-scale machines. The drilling rig was constructed from heavy-duty bamboo, with the drill suspended by cables. A team of workers stood on a wooden plank lever, much like a seesaw, and this lifted up the drill head made of iron. The pipe was allowed to drop until the drill bit on solid rock and began to pulverize it. The bamboo cable used in the machine was extremely strong. In fact, its tensile strength was comparable to modern-day steel. The drill stem was pulled from the hole using a large wheel, somewhat similar in appearance to that on a modern flexible cable downhole tool truck. This rig was extremely versatile. To deal with the different rock types, the Chinese even produced a series of drill bits, specifically modified to different geologies and rock types found in different parts of the country. Using these drilling techniques, workers were able to reach the depths of the earth, where salt, natural gas and oil were at their richest. When extracted from the wells, the gas was raised several meters above ground level, and then distributed for hundreds of kilometers through an elaborate network of pipes. But it was during the era of the Song dynasty at the turn of the first millennium that the pace of Chinese industrialization reached its peak. Inventors and engineers were creating colossal, incredibly advanced machines on a scale not to be seen in the West for another 1,000 years. And the techniques they invented for manufacturing are still in use today. As well as advances in technological engineering and manufacture, this period produced the earliest industrialization and mass production of a substance that was to change the world for good. The Song dynasty lasted from 960 to 1279 AD and was based in the Henan region of eastern China. The dynasty oversaw a 300-year period of economic growth, coupled with great artistic and intellectual achievement. It was during the Song period that the four great inventions of papermaking, printing, the compass, and gunpowder were further developed, technologies that spread across the world and changed it permanently. Of these four great inventions, perhaps the most significant legacy of the Song dynasty was the combination of three simple chemicals into one of the most explosive substances in history: gunpowder. This single-purpose but multi-use mixture not only revolutionized warfare, but has led to rocket and missile development and even the first few steps on a journey of exploration that has put man on the moon. But the Song period was also marked by stunning advances in manufacturing. One particularly innovative area was in heavy metal manufacture. In the province of Shantung, one recent discovery has given us remarkable insight into the metal forging capabilities of ancient China. The remains of a giant cast iron pagoda that dates back to the Song dynasty. What makes these iron structures so impressive is that casting massive pieces of iron is a challenge even today. How the engineers achieved this difficult task is something that we find hard to comprehend. To produce and cast quality iron on a mass scale, ironworkers today need to keep a massive volume of molten liquid at a very high temperature, so as to allow the pouring of the liquid metal. The same was true 2 millennia ago. One way to raise the temperature in a furnace is to blow in air, exactly as we might do when we fan the flames of a barbecue or use bellows on a fire. Modern ironworks use the same principle, but they use electrical air pumps to feed the fire. But how might the ancient Chinese have devised a method of driving massive volumes of air to heat their furnaces? Archaeologists have recently discovered evidence that automated air bellows machines were in fact in use. Drawing on the technological knowledge of their predecessors who had begun to use water as a motive power, it's now thought that Chinese engineers created a mechanical system for the operation of the blast furnace bellows.
To generate the kind of heat required in a blast furnace, you need quite considerable volume of air. It doesn't need to be incredibly high pressure, but there needs to be a lot of it. And what the Chinese did is they modified a traditional water mill, and they developed a system of bellows which were operated by cranks worked by the water-powered wheel.
Dr. Geraint Owen is a specialist in mechanical design and engineering at the University of Bath.
Using a water wheel as the starting power source, and you want to drive a bellows, you can drive it using a crank, and where you have a central axle and an offset pin and some form of connecting rod and link. So the water wheel will turn the crank in a rotary motion, and then all that the crank does with its connecting rod is convert that into a linear motion that you can use to power the bellows.
This type of machine is similar in principle to the design of the piston in a steam engine or automobile, but operating in reverse. In the Chinese machine, the wheel turns to operate a crank, whereas the later steam engine used a piston-driven crank to turn the wheel. The ancient Chinese understanding of engineering made possible automated continuous air blasts to create the high temperatures needed for successful iron casting. Hand in hand with the mastery of casting came further mechanical innovations that were also centuries ahead of their time. The Song dynasty produced advances in mass automated manufacture and high-tech sophisticated machines, some of which laid the groundwork for much modern machinery. One such invention is the ancient world's version of the odometer.
An odometer is a simple device that allows you to measure distance in exactly the same way as you have an odometer on the dash of your car.
But could the Chinese have invented the gearbox more than a millennium before the modern engine? This fascinating ancient device is known as the rangefinder chariot. When pulled alongside a marching army, the cart signalled the passing of each 500 meters by banging a drum. This model is a small-scale version. The actual odometer was much larger.
The real-size chariot is very big. What you see now is a mini-sized model. We rebuilt this according to the ancient texts.
The toothed gears in the machine are driven by the chariot's wheel. It uses what is described by modern engineers as a reduction gear train, a system that lowers the output speed so that one or more pins can revolve slowly, releasing catches at predetermined intervals to trigger the striking of the drums every 500 meters. Experts believe that the machine was used to lead the Emperor's royal guards on military assignments, to record the distances of enemy camps, and to measure how far the army had marched from the royal city.
When the wheel outside is turned, it drives a small standing gear wheel inside. The large gear wheel drives a small gear flywheel, which again drives a large wheel. A lever on the big wheel will trigger the string to hit the drum when the wheel has turned enough. Now the little lever is in a position to be triggered. It is triggered and the string on the drum is hit.
What is remarkable about this odometer is that its gear systems match precisely those in today's motorcycle engines.
One of the keys to the range-finding chariot was the gear system within it, and here is an example showing a section motorcycle engine, and this engine is currently in bottom gear, and you can see that you need a number of turns of the engine in order to make the output sprocket of the motorcycle go along. So this is gearing down the speed of the engine to the speed of the sprocket. The same would have happened in the range-finding chariot, only that it would have been an even greater reduction, so that you would have had for every 500 yards, the main wheel with the trigger would have just turned once.
This type of machinery demonstrates that the Chinese possessed an early understanding of the elements that are used in jackwork in today's modes of transport. But there is intriguing evidence of the application of gear engineering on a massive industrial scale during the Song dynasty. One discovery in particular has caused scholars to rethink their views on ancient manufacturing. And we now know that the Chinese had fully operational, huge factories capable of mass production. The zenith of ancient Chinese innovation took place under the Song dynasty, which lasted from 960 to 1279 AD and was based in eastern China. This was a 300-year period of incredible inventions and machines. They revolutionized warfare and even led to man exploring space, using navigational instruments that guided mankind's journey of discovery. Only now are we discovering that these intriguing machines fundamentally match the principles of today's modern technology, causing us to ask, did we invent modern machines, or did we just reinvent them? At the height of the Song dynasty in the 11th century, huge cities had begun to develop that were centers for trade, industry, and commerce. With populations of hundreds of thousands, they required automated machines that could increase the output of production. One such ancient industrial machine, recently discovered by archaeologists, is the hydraulic trip hammer, believed to have first been developed 2 millennia ago. Today, in the province of Jingdeshen, an example of this extraordinary ancient technology is still in use, a testament to the machine's effective design.
A trip hammer is a good example of one of these water wheel powered devices. Basically, you have a large mass that is supported by a cam, and as the cam is rotated, the mass is lifted, and then the mass is allowed to fall.
The system was amazingly advanced for its time. The machine actually consisted of several hammers, which were operated by a series of cams or lugs on the main revolving shaft. The hydraulic machine converts the kinetic and gravitational potential energy stored in running water into rotational power in a water wheel. The wheel is attached to a long transverse axle. There are several wooden boards inserted into the revolving shaft, with each board controlling one hammer. The wheel causes the shaft to rotate, which in turn moves the lugs. As they turn, these lift the hammers. When they have turned 60 degrees and the hammer is at full height, they release the heavy mallet, which falls and pounds the material below. Each hammer could crush up to 50 kilos of force, meaning that all 8 hammers could operate a total of 400 kilos of force in a single rotation. The ancient texts tell us that this mega machine was adapted to not only crush grain, but to pound metal in industrialized automated metal workshops, just as is still done today.
The labour-saving potential is enormous. Instead of perhaps having to have 5 or 6 blacksmiths, each with a 10-pound sledgehammer, you could have one 70, 80, 100-pound, 200-pound mass being lifted and dropped a considerably bigger distance. And this could be then used by just 1 or perhaps 2 men working, and that saves you labour but enables you to make bigger things as well.
Today, the remains of mega water wheels that powered the hammers still litter the landscapes of rural provinces, offering a fascinating glimpse of what these hydraulic machines actually looked like. But the Chinese soon invented a more efficient way to grind grains, using millstones. The grain is crushed under a massive stone weight. This is a tried and tested technique, but the ancient Chinese took the technology to an advanced level. This machine is called the multiple-geared grist mill. As with the trip hammer machine, the multiple-geared mill was also powered by water. However, this machine harnessed the power of the water wheel to drive a complex angled gearing system and power 9 separate 2-ton millstones. Remarkably, the engineers devised an advanced system that transferred the water power via the drive shaft across a 90-degree angle change to drive the millstones.
We have this one enormous wheel which has got a shaft fixed to it, and on this shaft are a whole series of gears which are providing the motive power, and then from these there are a series of right angle gears which are changing the direction of the rotation and allows a whole series of different millstones to be driven off one shaft. This is a very economical way of generating the required power.
The extraordinary thing about this type of ancient Chinese gear-powered water mill is that it incorporated technology not to be seen again for nearly 1,000 years.
What we're looking at really is almost a precursor of the Industrial Revolution. This was industrialisation on a scale which we would recognise today.
The sophistication of ancient Chinese gear technology was highly advanced, and there's more evidence that the Chinese had a long tradition of ingenious geared machines. Beautiful, engraved jade rings were discovered in tombs dating back to 400 BC. Their spiral design has intrigued scholars. After studying their design, archaeologists now believe that the only possible way to produce the precision spirals must have been by using a machine. A device known as a compound machine is one that synchronizes rotational with linear motion. This means that as one part of the machine turns the disc, the other draws the line in perfect synchronicity, with a geometric accuracy that is impossible to achieve by hand. Richard Windley has been studying the Chinese rings and has created a compound machine capable of such precision designs.
To produce this kind of curvature would really need a machine which was capable of rotating and moving in a linear fashion at the same time. This is what we call a compound machine. I've actually built a small model which will demonstrate this process. It consists of a turntable on which a blank or disc to be marked out is mounted, and a linear rod which moves across it. This rod holds the pen which is going to mark out the spirals, and by moving the rod backwards and forwards, the pen traverses the blank as the blank is actually rotating, and this produces what is known as a true Archimedean spiral. But what we also have is a gearing system which relates the movement of this bar and the movement of the turntable in a very controlled mathematical method.
There are 2 uprights attached to the end of the bar that moves the pen across the blank. These uprights are attached to a string that is wound round a disc under the device. So as the bar moves back and forth, the string turns the disc in perfect sync. It is this disc that rotates the blank and creates the perfectly synchronized designs.
I'm now going to load the little bamboo brush with drawing ink. Since these rings would have a series of flutes, they varied in number. In my case, I've got 8 divisions, so we'll repeat this 8 times, and that should give us the perfect, complete design.
We now know that this type of compound machine may have been used either to mark up the jade or by the direct action of a diamond-tipped stylus. Over thousands of years, technological innovations filtered slowly but steadily from east to west, carried through Central Asia over the 6,000-kilometer Silk Route. But there's an extraordinary archaeological site that provides us with a unique insight into the capabilities of ancient Chinese engineers and craftsmen. The first emperor of China's terracotta army is startling evidence of the magnificence and grandeur of the ancient world. Located near Xi'an in eastern China, It is considered by many to be the 8th wonder of the ancient world.
The discovery of this tomb and the excavation of it is one of the top archaeological finds of the whole world. It's as important as the pyramids, if not more important, and though there are many, many tombs in China, nothing like this scale is seen in any other part of China.
Buried near the Emperor Qin's tomb, to defend him in the afterlife, ancient Chinese craftsmen and engineers created over 8,000 warrior statues of breathtaking quality. Even more extraordinary is that these warriors are actually armed, with over 10,000 fully functioning, lethal bronze weapons. Warriors of the age would have used copies of these exact weapons when they engaged in hand-to-hand combat. More than 2,000 years later, they still have the capacity to inflict enormous damage. Archaeologists believe that these weapons, along with the warriors themselves and their body armor, were mass-produced in ancient factories. But how did the emperor's engineers approach the complexities of high-quality mass production? And what technology was used to create some of the world's most beautiful and impressive objects?
Each figure is individually sculpted, cast, polished, showing the sort of production techniques which were not generally introduced in Europe until the 18th century.
The sheer scale of the discovery is mind-blowing, and even today, some 30 years after the discovery, archaeologists are still uncovering hundreds of ancient weapons and artifacts. Arguably the most impressive finds from the excavations so far are the emperor's chariots. It's thought that these full-scale vehicles were to have been used for the emperor's inspection tours in his afterlife. Investigations into their production have revealed that during the Qin dynasty, the Chinese, through careful practice and detailed research, had established highly advanced scientific standards for metallurgy and metal production.
The bronze chariot could indeed present the highest achievement during the bronze casting history in ancient China. These two chariots were each made of 3,000 components. Every single component was made alone and combined together later with others.
In total, the emperor's chariots comprise 3,642 separate parts of gold, silver or bronze. What is particularly remarkable is that each was individually cast before assembly. It would have been like hand carving all the pieces of a 3,500-piece jigsaw puzzle separately, whilst never being able to match each piece to its neighbors until the project was complete, all the while ensuring the fit was perfect. Most of the joins were made using a technique known as cast welding. Welding is the technique of joining two pieces of metal using extremely high temperatures and a solder to create a very strong bond. Cast welding of iron is very difficult even today, as cast iron has a carbon content 10 times that of steel, and this high carbon content causes the metal to flake. Managing the temperature of the process is critical, and this requires a highly advanced knowledge of temperatures and the properties of metals. Inlaying was also used. This complicated process involves inserting a piece of one metal into a slot in another, a challenging technique that the ancient Chinese mastered. These were highly advanced processes that we still use today.
I think the bronze chariots were not only an unprecedented achievement at the period, but also an achievement that could not be surpassed by any in the later dynasty and eras.
The chariots and horses are the largest find of fine bronzeware discovered in the history of world archaeology. But the emperor's chariots are not alone in revealing the sophisticated technology and engineering in use more than 2,000 years ago. Every single soldier of the Imperial Guard was armed. Archaeologists at the site have unearthed an array of weapons including spearheads, crossbow bolts, crossbow trigger mechanisms, blades of dagger axes that would have been mounted on 3-meter poles, and almost meter-long swords that are still razor-sharp. The sheer number of weapons suggests that vast factories and workshops were in operation on a level of industrialization to match the factories of modern industrial cities. With meticulous detail, each weapon was cast and modeled to its standard shape, and then filed, chiseled, drilled, and polished. But there's one question that remains behind the discoveries of these marvelous ancient weapons. Why, after 2,000 years, do these bronze weapons still glitter? And how did the ancients create such metals that still preserve their strength and sharpness? Using state-of-the-art electron probe microanalysis, archaeologists believe that the key to unlocking this ancient mystery may lie in the discovery of a dark grey layer covering the weapon's surface. Incredibly, the layer has been identified as chromium, a highly complex protective layer that wasn't developed in the West until the 1930s.
2,000 years ago, in the Qin era, they'd already mastered the use of chromium. In the modern world, the technology to oxidize chromium was invented in Germany in the 1930s and in America in the 1950s. In China, this was put into practice very skillfully. It is a remarkable achievement.
As research into the weapons continues, will further discoveries be made that will cause us to reopen the history books on the development of highly complex materials? Despite the incredible advancement of the weaponry, it is the terracotta army itself that remains a mystery to modern scholars. How were the soldiers mass-produced on such an enormous scale, and to such an exquisite level of craftsmanship and casting skill? This accomplishment has stood the test of millennia.
The making of the terracotta warriors is a real example of how China ran a semi-industrial society. In order to build this tomb, the emperor summoned 700,000 people to work at the site, and they probably worked for 10 years, possibly longer.
This massive labor force is the modern-day equivalent of 40 car factories. Its organization alone must have required extraordinary skill and foresight. In Lingtong province, close to the emperor's tomb, a replication company has undertaken the challenge of recreating the warriors using ancient materials.
I think it is a very difficult thing to do even nowadays. To make figures in the ancient time was much more complicated. Using the clay rolled production method at the time, it would take 20 days for the whole process.
Once the clay is rolled, the artist builds the main structure of the warrior's body. Each figure is then sculpted with armor and his own facial expression. Modern-day workshops repeating the production process have found that each warrior figure requires on average 130 kilos of clay, meaning that the craftsmen who created the terracotta army needed in the region of well over 1,000 tons of clay. No kilns have so far been discovered at the site, and the firing process remains an ancient enigma for archaeologists. Some scholars now believe that the molds of the warriors were encased within a temporary shell and were fired using a traditional kiln technique that reached temperatures of over 500 degrees.
A project of this scale at the time would have required large kilns. But it's a great shame that none have been discovered so far.
Once the temperature has climbed to its maximum, the mud surface of the temporary shell cracks, allowing hot air to glaze and harden the figure. The results after removing the shell are remarkable and offer a fascinating insight into the advanced understanding of ceramic technology that was developed in ancient China over 2,000 years ago. What other mysteries will archaeologists uncover at this spectacular site? Ancient China was not only responsible for developing industrial machines and practices, for there was one inventor during the Song dynasty who created a machine that is nothing short of stunning. This machine was to cement China's reputation as being at the forefront of ancient technology. It was known as the cosmic engine, the ancient world's astronomical computer. Although the inventors of ancient China developed a vast range of mind-boggling technologies, there is one invention that stands alone as the embodiment of Chinese expertise in science and engineering. And as was the case with the Romans and the Greeks, it was built by a Chinese innovator who was way ahead of his time. A master of precision technology and a brilliant all-round engineer, his name was Su Song. Su Song's most amazing invention was so complicated that for centuries its workings were an enigma to engineers and scholars. It was simply called the cosmic engine. In effect, a huge, water-controlled astronomical cosmic computer. It was such an incredible feat of engineering and scientific knowledge that few Westerners believed it could have existed.
Su Song's water-driven cosmic engine was created in 1092 AD. It was considered to be one of the most splendid achievements in the history of ancient Chinese inventions.
Su Song's complex mechanism was designed to calculate time, not just hours and minutes, but weeks, months, and seasons. The ancient Chinese understood that the calendar reflects the way the Earth moves around the sun. But what makes this machine truly stand apart is that the cosmic engine also calculated the way the Earth and planets move through space. Furthermore, the ancient Chinese believed that the movements of the stars were closely related to the destiny of the country and its rulers. This 13th century observatory in Henan province is the oldest surviving observatory in China. Even today, when the sun reaches its zenith, rays beam down this central drain.
After the rule of the Yuan dynasty unified China, he wanted to improve the development of agriculture. They want to make a reform of the old calendar so they can know the time when the farmers plant the corn. And every day he measured the shadow of the sun and made some recorder of the changes of the sun. Then according to the recorder, he made out a calendar. The calendar tells us it will take 365 days, 5 hours, 49 minutes and 12 seconds for the sun to go around the Earth.
But 2 centuries before this impressive observatory was built, Su Song was well on his way to designing and then building his astronomical computer. This machine was not only to calculate the passage of the stars and the Earth in order to tell time, it was to reveal to the world the technological sophistication of China. This was a monumental task. How did Su Song realize such an ambition?
The cosmic engine is a huge 12-meter tall apparatus and very complicated inside. It includes 4 major systems built up by more than 400 parts. It is a masterpiece of mechanical design and manufacturing.
Today, we know exactly how this mechanism was built because Su Song left us detailed blueprints in his treatise called A New Design for a Mechanized Armillary Sphere and Celestial Globe. The book was written 900 years ago.
This book is very precious to us today. It gives us the original blueprint, so researchers can clearly see the configuration of this ancient apparatus. The script contains 47 illustrations. These include all the parts and their assemblage.
The Science and Technology Museum in Beijing, using the machine's original blueprint, has built a fully accurate reconstruction. The computer looked like a tower. The whole mechanism was 5 stories tall. The front of the tower was a pagoda structure, with each of the 5 stories having a door through which mannequins appeared ringing bells and gongs and holding tablets to indicate the hours and other times of the day and night. But how did it work? What ingenious innovations and technological developments were involved? A celestial globe showing the movement of the stars inside the tower turned in synchronization with a sphere just above it. As the celestial globe turns, so does the sphere. This meant that the analysts and engineers using the computer could compare and cross-reference between both globes and record multiple data. All of the time indicators were controlled by the same giant machinery that simultaneously turned the sphere and the globe. Within the mechanism is the earliest example of an escapement in a machine, a concept essential to modern mechanical clockwork. In any form of clock-based machinery, power must be delivered to the mechanism in a precise fashion that can be accurately regulated. The rationing of power is the function of this escapement and is something Susong successfully achieved. Susong included a cogged wheel in the system. Connected to this was a stopper that only allowed the cog to rotate at a specific rate, by stopping the rotation briefly and then allowing it to continue at a precise, regular frequency. It is this ingenious system that allowed the invention of Western clocks centuries later. And in fact, it is the periodic stopping and releasing of the escapement that causes the ticking sound of any clock or timer today. Another ingenious aspect to the cosmic engine was its power source, a great scoop wheel using water and turning all the shafts, working the various devices. This ancient super machine ran from the 11th century until it was destroyed by political enemies of the Song dynasty. The cosmic engine is considered by some scholars to be the greatest mechanical achievement of the Middle Ages anywhere in the world. The Song dynasty left a legacy to science and technology, engineering and industrialization that changed the world irreversibly. Although ancient Chinese history is littered with evidence of complex machines, many ingenious designs were literally inconceivable to Westerners of the time. Today, the decoding of texts and archaeological investigations have forced us to admit that many of the inventions and discoveries upon which the modern world rests come from the great minds of ancient China. Should we rewrite the history books? And should we rethink everything we thought we knew about the ancient world? The instrument for inquiring into the wind and the shaking of the earth.
The seismograph isn't quite as modern an invention as people perceive. It was invented 2,000 years ago in China. Chan Heng's invention was probably something like 1,600 years ahead of what was done in the West.
Today, the Earthquake Administration in Beijing uses digital technology to record ground-shaking tremors over large bands of frequencies and seismic amplitudes. And an early warning earthquake system was just as essential in the past. News traveled slowly across the vast state. How could news of an earthquake be passed to rescuers quickly? Chang Heng's seismograph was the answer.
The device consisted mainly of a massive bronze vessel. This was reputed to be about 6 feet across.
The earthquake machine was a huge vessel of cast bronze, consisting of 9 dragons facing outward in a circle. Each dragon gingerly held a ball in its jaws. The instrument was designed so that any seismic tremor would cause the ball to fall from the jaws of the dragon and into the mouth of a frog facing the direction of the tremor. Despite its beautiful exterior, it is the internal mechanism of the machine that is so ingenious, even by today's standards.
When an earthquake struck, the vibration which was transmitted through the earth, which actually travels very, very quickly through the earth's surface, would hit the jar.
There was a vertical rod inside the jar, carefully balanced with a weight at its top end. This is known as an inverted pendulum.
The seismograph worked by having an inverted pendulum inside it that basically toppled over, and by toppling over in one direction or another, it would impact with a ball, and the ball would fall from the side of the seismograph, giving an indication from which direction the earthquake had actually come.
The inverted pendulum is an ingenious device. It stands motionless until the slightest vibration sends it toppling over, indicating the direction of the epicenter.
We can all picture what a conventional pendulum is. If we think of a grandfather clock swinging, it has a pendulum swinging inside it. An inverted pendulum is the exact opposite, where you have a pivot underneath and you're trying to balance that from underneath.
But there's another discovery from ancient China that, like the seismograph, is vital to us today. A technology that delivers the ultimate power source of the modern world, oil drilling. Today we assume that it was modern engineers who pioneered the art of deep drilling technology. Yet incredibly, the techniques used in acquiring supplies of oil and natural gas were actually reinvented from those of the Chinese 2,000 years ago.
It's amazing to think that it's 2,000 years ago the Chinese were using the same techniques to drill for salt and for natural gas that we're still using today.
The sheer size of the ancient drilling machines was remarkable. Derricks, also known as Heron carts, rose over 50 meters above the ground. Images which we associate today with the landscape of Texas would not have been uncommon in ancient China. Amazingly, examples of these ancient industrial machines still exist in some regions of China. This allows scholars a first-hand glimpse of the devices used in these ingenious, super-scale machines. The drilling rig was constructed from heavy-duty bamboo, with the drill suspended by cables. A team of workers stood on a wooden plank lever, much like a seesaw, and this lifted up the drill head made of iron. The pipe was allowed to drop until the drill bit on solid rock and began to pulverize it. The bamboo cable used in the machine was extremely planets and the stars, and even blast furnaces capable of forging metal on a scale that rivals that of the modern world. Some of these technologies were so complex that for centuries they remained a mystery.
China was always an immense state, much more unified than Europe at the same time. If they were to control the population, they had to organize manufacturing on a very large scale. I regard that as the basis of industrialization.
But how did the technology of China become so advanced? And who were the ancient inventors that designed and built these complex and awe-inspiring machines? This ancient text provides a clue. It describes in detail something that is still needed in modern times, but was actually invented nearly 2 millennia ago. It is a seismograph, an earthquake-detecting machine. It was designed and built by the master inventor Chang Heng. Chang Heng, who lived during the time of the Romans, rivals Archimedes and Leonardo da Vinci as one of the greatest geniuses of the past. In the 2nd century AD, he designed the Hufeng Daidongyi. It's a common assumption that the machines that power our lives were invented by us in modern times. But is this true? Today, new discoveries from the ancient world are forcing us to reconsider and to rethink the development of mechanical science. And what we are discovering is leading scholars to go back and rewrite the history books. These are the machines of ancient China. While Europe endured the so-called Dark Ages, ancient China reigned supreme as the world's technological superpower. Only now are we discovering that many of the inventions that shape our modern world have their roots in this remarkable Oriental civilization. Complex geared machines that allowed production on an industrial scale. Precision seismographs for detecting earthquakes. Drilling machines that bored for natural gas hundreds of meters beneath the Earth. The cosmic engine, a super-scale astronomical computer that not only told the time, but also predicted the passage of the